In this lecture, we'll conclude our discussion on algorithms, and we'll do this by taking a look at a few algorithms that take longer than linear time. Recall that we had a sequential search algorithm, and this simply searched a list of n items and it took theta of n time. Well, that was fine and all, but there are better algorithms for searching. In fact, we're going to take a look at the binary search algorithm. So this is a lot more efficient than the sequential search algorithm. But the trick here is that it only works if the list is already sorted. So if it's an unsorted list, this isn't going to work. The high-level idea is that we're going to start at the middle of the list instead of the very beginning. Because the point here is that we don't need to check every single item. So we'll start the middle. If the middle item happens to be the item that we're looking for, then we're done. We just say we stop, we found it. Now, if it's not, then what we're looking for must either come before the middle item or after the middle item. Because remember, the list is sorted. Now, if it comes before the middle item, then we're only going to consider the first half of the list. We don't need to look at the second half because it's not going to be any of those values, so we can just eliminate those. Now, if what we're looking for comes after the middle, then we will consider only the second half of the list. We don't need to take a look at the first half of the list. None of those items are going to be what we're looking for, so we can just eliminate those. And then we just simply repeat all of the above with the new list. So we'll take a look at the middle item of the new list. We'll check to see if it's that value, and if it's not, we'll see if it comes before or after. And depending on which one it is, we'll only consider that portion of the list, and we'll just keep repeating until we either find what we're looking for or conclude that it does not exist in our list. Let's take a look at the binary search algorithm. So it starts off just like our sequential search. So we need our name, the size of our list, the list of names themselves, and the list of phone numbers. We need to set the value of beginning to 1 and set the value of found to no. And then we're also going to set a value called end, and we're going to set that to end. So beginning and end give us the beginning parts and end parts of the list that we're considering. So as long as found is no, so as long as we haven't found the person, and beginning is less than or equal to end, because the way we're going to do this is we're going to change beginning and end, and it's possible that those two values cross over. So if we cross over, then that means we haven't found the person we're looking for, and we've exhausted the list pretty much. So as long as these things haven't happened, then we're going to go through steps 5 through 10. So we're going to get the middle value. So we're going to set a value m to the middle value that's between beginning and end. And if the name is equal to nm, then we'll print the phone number tm and we'll set found to yes. Now, if that's not the case, then that means the name that we're looking for, so name either comes before nm or after nm. So depending on that case, we're going to change either the beginning or the end. So if name precedes nm, so if it comes before nm, then that means we're going to set n to m minus 1. We don't set it to m because we know m's not what we're looking for, so we only need to consider the list from items 1 to m minus 1. Now, if this isn't true and name follows nm alphabetically, then we're going to set beginning to m plus 1. So we only want to look at the items in the list starting from m plus 1 all the way to the end. So we'll just keep repeating this until we get out of the loop. Now, if we get out of the loop and found is still no, then that means that the name isn't in the directory. Let's run an example of the binary search algorithm with this list of names. And let's say in this case we want to search for the name Cora. So what we're going to do is we're going to set beginning to 1 and we're going to set end to 7. So I'm just going to use capital letters here. So here is our beginning. It's going to be right here. That's not a good B. Let's try this one more time. All right, that's the best we're going to do. And then we're going to set end over here. So there's our beginnings at 1, our end is at 7. So our midpoint is going to be at 4. So right here, right in the middle. So here, Cora is not Devi, so we haven't found the name yet, but Cora precedes Devi, or it comes before Devi. So we're going to set end to 4 minus 1, which is 3. So we're going to set our endpoint to right here, and we're going to eliminate this whole portion of our list. So here's the remainder of our list. So once again, we would set a beginning here at 1, so that hasn't changed, and our end is going to be over at 3. So that means our midpoint is now at 2. And we see that Bob is not Cora, but Cora does follow Bob. It does come afterwards. So we're going to change our beginning to 2 plus 1, which is 3. So now what's going to happen is we're going to remove this portion of the list. So this is the remainder of our list. And, well, yeah, it's one item, so we're going to see that it's either this person or not. But the midpoint here is going to be 3 because it's both the beginning and the end. So technically, beginning and end are the same spots. And we do see that Cora is in this spot. So we would set found to yes. So sure enough, Cora does exist in our list. So now let's analyze the binary search algorithm. So we need to ask ourselves, how many comparisons do we make in this list? Well, it's not n, because otherwise we'd be looking at every single item in the list. So we're not doing that. But instead, every time we do a comparison, we're going to cut the size of our list pretty much in half. So the question then is, how many times do we actually cut the list in half? So the way we get this is we can compute the logarithm of n to base 2. And we denote this as either log n or log base 2n. For our purposes, they pretty much mean the same thing. Now, what is the logarithm of n in this case? Or what is log n? Well, just to kind of give you an idea, if we say log n equals m, this is the equivalent to saying that 2 power m equals n. So in this case, we can use this log to determine how many times we're going to cut the list. So since we have log n comparisons, or since we're cutting the list in half log n times, our algorithm in this case is of order of magnitude log n, which we denote as theta of log of n. So how does sequential search compare with binary search? We said that binary search is faster than sequential search. Now this is true if the list is already sorted. So let's take a look at some examples just to show you how much better binary search is. So let's say n is 100. So if we do a sequential search, this is going to take about 100 comparisons. Now what about binary search? Remember, the number of comparisons is going to be how many times we cut the list in half, or log base 2 of n. Well, log base 2 of 100 is about 7 comparisons. So that's pretty good when you think about it. I mean, 100 comparisons versus 7, that's a pretty good difference. Let's try something a little bit bigger, just to kind of give you an idea. Let's say n is 1 million. We're searching for 1 million things. If we do a sequential search, well, that's going to take about 1 million comparisons, because we're looking at each item in the worst case scenario. What about binary search? Well, so what is log base 2 of 1 million? It's about 20 comparisons. So just think about that for a second. If your list is sorted, you can find what you're looking for or determine whether or not it exists in your list with just 20 comparisons for a list of 1 million. That's huge. That just kind of shows you how powerful log n is compared to n. Now let's take a look at our pattern matching algorithm that we talked about before. So in case you don't remember how that worked, we want to find all occurrences of a pattern of some form which we denote as P1, P2 all the way to Pm within a text that's of the form T1, T2 all the way to Tn. So how did we go about doing this? Well, at each position, we'll just simply try to match our pattern with the text. And then if it's there, then we say we found a match there. And then we move on to the next position and we repeat this. So we'll start at position 1, then we'll check the pattern at position 2, position 3, and we stop after position n minus m plus 1. So let's analyze this for just a minute. We'll ask ourselves first, what is the best case scenario? And you might think, well, wait a minute, don't we look at the worst case scenario? Well, don't worry, we're going to get to that in just a second. But let's first ask ourselves, what's the best case scenario? And in this case, it's actually that we find no matches. And in this case, what happens is the first character never matches. So we just look, we see there's no match. We go to the next one, we see there's no match. So for example, let's say our text is KLMNPQRSTX and our pattern is ABC. we find that there is no A in here. So we'll just go through this list, this text, I should say, very quickly and find that there are no matches. Now, what is the worst case scenario? Well, it's also when we don't have any matches. And you might think, well, how can both the best case and worst case scenarios be when the pattern is not in the text at all? Well, the difference is on exactly how the pattern fails to be in the text. The best case occurred if the first character of the pattern was nowhere in the text. But in the worst case scenario, everything but the last character in the pattern matches. So like for example, we may have the text being all A's, but then our pattern is AAAB. So we're going to go through every single one and we're going to check all but the last character in the pattern to find that it does not match. So I mean, this is the absolute worst case scenario. Another worst case scenario is if everything matches. So if our pattern is AAAA, we're going to compare every single character of the pattern with every single character in the text. So both of these would be considered worst case scenarios. Let's analyze this algorithm real quickly. So we want to consider the worst case scenario. And in both cases for the worst case scenario, what's going to happen is for each character in the text, we check just about, if not all, the characters in the pattern. Well, our text has n characters and our pattern has m characters. So that means the total number of comparisons is going to be m times n, or we just say mn to simplify it. So that means our algorithm here takes theta of mn time. And this is the first case where we see that our asymptotic time is based on two different inputs, the size of our text and the size of our pattern. So it's quite common where we could encounter some algorithms where we have multiple inputs and the sizes of both of those or multiple inputs determine the running time of our algorithm. So like in this case, we have two inputs, the pattern and the text. So our algorithm here is theta of mn time.